Hello all, good morning. This is this is Prathamesh. I work as senior data scientist for text analytics, natural language processing, and artificial intelligence at Merck Life Science India, also known as Merck Group across the globe. And I would like to thank John Snow Labs and all the organizers of NLP Summit Healthcare for giving me the opportunity to present one of our use case that we are working or worked as part of our organization's opportunity to work in the area of COVID-19 literature search engine. So today we'll spend approximately next 30 minutes or so to understand how we developed an NLP and deep learning driven literature search engine that can help and is helping our experts within our organization to identify and extract relevant COVID-19 related information from the different literature which is being published. So straight away jumping into the presentation. Today we'll discuss about our approach. Of course, introducing what are some of the challenges or the business objective that we kept in front of us just to formalize the problem statement and develop solutions accordingly. Then we will walk you through the semantic search engine that we developed, and finally some of the approaches that we used in the area of universal sentence encoding and Facebook's recent search capability that they open source. And also we have an enterprise solution within our organization as Elasticsearch for indexing and storing the textual data into the NoSQL database. So we also did a comparative analysis and study in terms of how the Elasticsearch recent version which offers embeddings as a service, along with how it is comparing against the Facebook's recent search capability that they open source. And then finally, we'll walk through the outcomes of the COVID data challenge that we participated in. So recently, National Institute of Standards and Technology, which is also known as NIST, had organized a data challenge or a competition in the area of COVID-19. So how we kind of did there, will also do a quick overview of that. And then finally, due to the sensitivity of the data and the, of course, not data, but essentially the sensitivity of our organization's network, we may not be able to show you the actual system, but still we will give you the glimpse of it. And then finally, what are our next steps in this direction? So quickly moving on to the background or the introduction. Fundamentally, we all know that we have a growing risk of fast-paced spread of COVID-19 across the globe. So we are getting second wave, third wave, and it's kind of continuing. So as a human being or as an organization or as the governing bodies across the organizations, all of us are doing everything and anything that is in the power. We are trying to stop the spread via the stoppage of travel, via the stoppage of schools or lockdowns, mini lockdowns, etc., just to break the chain, if not cure, because of course we all know that some of the organizations or non-governing organizations and universities are working in the area of vaccine, but still the vaccine is in the research phase and a lot of companies are trying to get there, but still we have to break that chain. So to do that, we are studying and we are looking at various different researches, literatures which is published across the globe. So it's not necessarily about COVID-19, it can be about the past epidemics or pandemics which kind of shook the world. So fundamentally, we are trying to understand what kind of decisions were taken at that time to stop the spread, and which is also very valuable. But the challenge is that these research articles or the literature articles are lengthy in nature, and a human has to read through it to understand what kind of takeaway can be received or can be used out of it, or then how we can further make it into an actionable insight or an actionable decision. So to do that, we as AI and NLP researchers want to bring in this, the idea of using the techniques of natural language processing, deep learning, to fundamentally give an engine which can automatically look through all these different literature articles which are being published across the globe. And as we speak, they're still getting published. And then use those ideas or any data points that we identify out of it, basically to control the spread via either medical or non-pharma intervention. So it can be about the stoppage of travel, or it can be, let's say, a closure of schools, or it can be a very typical medical-driven literature as well, in the area of vaccine, in the area of let's say, efficacy of vaccine on diabetic patient or impact of COVID-19 on diabetic patients or pregnant women, etc. So with this, we want to bring this engine and this approach where we want to help community members to find the right literature using the methods of NLP. So just to set a business challenge, because it is a huge and it's a vast problem to solve. If you want to build a search engine, it has to set a clear expectation and clear boundaries in terms of what we want to solve and what we want to achieve. So essentially, the idea was that we develop an engine which leverages techniques of artificial intelligence, state-of-the-art techniques of text analytics and NLP. And we want to understand and identify what are some of the known factors in certain measures in the communities like lockdown. So what are the potential impacts on it, and how we can ensure that the citizens or the people of different countries are compliant to it, because we have various different populations across the globe. So it has to be very accurate and compliant too. And of course, understanding some of the examples like how efficient it was when we closed the schools, when we did travel bans, when we stopped the mass gatherings of various sizes, we adopted the techniques of social distancing. So was it helpful or not? And at the same time, understanding techniques, whether vaccine is helpful, what are the stages of vaccine, where the vaccine is currently. So it can be a vaccine which is kind of researched by University of Oxford, or it can be anyone's vaccine. So we want to understand the different perspectives out of the literature. But again, the challenge is that we have widespread unstructured data, and it becomes kind of very critical and kind of becomes very tricky to understand everything out of these different literature articles. So if we now get closer to the solution, we first want to understand what kind of data that we used. So we approximately looked at 120,000 articles, and as we speak, they're still getting published. A lot of different government, non-government organizations are doing research in this area, and they are publishing. But the source for these particular data points is PubMed's PMC, PubMed Central Open Access Corpus, wherein we receive the data using the queries like COVID-19, coronavirus research, etc. And also we are looking at the additional research articles which are also maintained by WHO, because they also have their own separate corpus. And at the same time, we are looking at preprints of bioRxiv and medRxiv as an additional data source to look at. So we are looking at data for almost last 20 years. So when we say 2020, when we know that articles are still getting published, so we continuously update or improve the system. And of course, the data is kind of maintained and created by Microsoft Research, then Zuckerberg Initiative, Georgetown University Center for Security and Emerging Technology, etc. So a lot of different organizations are contributing to creation of this data, just to see what kind of techniques can be applied on this data. So this is just a snapshot of data that we used. Now, this basically is a high-level view of what we developed as a system. So as a user, if I put myself in the place of this business user, I can do three different things. That's why you would see markings as phase 1, phase 2, and phase 3, where we have completed the phase 1, and phase 2 is currently under research, and phase 3 is the next step that we want to achieve, which is like a ultimate phase of doing a search or doing retraining based on expert feedback using techniques of reinforcement learning, etc. So if we see phase 1, fundamentally we have a component which is doing a query resolution. So essentially we are trying to do the query resolution engine. We are trying to do we are trying to understand what kind of query it is and what kind of information we receive. So fundamentally it's about understanding what kind of information user is requesting for, whether it's about vaccine, whether it's about a spread within the different regions. So we want to understand that. So we have a NLU search and mining engine, which is fundamentally doing a deep dive into what user is asking. So essentially slicing and dicing the question so that we can fundamentally understand how the different articles are linked to each other in terms of, let's say, relevance, in terms of, let's say, context, in terms of, let's say, various entities like vaccine, COVID-19, impact of COVID-19 on pregnant women, etc. So this is fundamentally decoding the query from natural language into some form of a vector, which can be applied onto the embedding space where we are trying to do a search. So now these embeddings are generated using USC, and they are indexed as part of the Facebook's recent open source technique called FAISS, as well as Elasticsearch. So these are the embeddings which are helping us understand for what kind of question, how the embeddings are linked to each other. And then finally, we are looking at data coming from PDFs, HTML files, XML files, study reports, emails, etc. So we kind of call this as a dynamic knowledge embeddings, which are using the techniques of artificial intelligence. And finally, some form of knowledge base, because ultimately we need some dictionary to ensure that it is not biased towards something else, and it is kind of taking the human intelligence too. So that's how it's kind of fetching the information. And then we have the source of PubMed, WHO's dataset, and BioRxiv and MedRxiv. So this is something that we developed as part of phase 1. And subsequently, as we proceed to the next slides, we'll also see a glimpse of what we are trying to do in phase 2 and phase 3. But essentially, we are trying to envision this as a larger system. Now, further doing a deep dive into what we did. So essentially, we started with the techniques of FAISS and USC. So FAISS stands for Facebook Artificial Intelligence Semantic Search, and USC, of course, stands for Universal Sentence Encoder, where we are trying to develop embeddings or generate embeddings based on the documents or literature articles that we have. So if we look at this as a flow of information, we have a data set which consists of approximately 120,000 research articles. So we use techniques of NLTK, JSON parsing, and theme extractor. So we have an in-house proprietary algorithm on extracting the themes to identify the context from the dataset, which is kind of separating the individual documents from the overall dataset. And then we are applying the Google's Universal Sentence Encoder on top of these individual documents. So when we say documents, it can be either a set of sentences, it can be either a set of paragraphs, or it can be a whole document itself. So we experimented with sentences so that we can understand what kind of semantics are mentioned, but definitely we can also experiment with paragraphs too. So essentially we generate embeddings, and then those embeddings are fed to the FAISS, which is basically the search technique that Facebook has launched. So if we see it in the real time, how this might happen. So user is passing in a query into natural language, so it can be in any form and shape. We on the fly apply USC on top of the query. We determine the query embeddings, and we search against the FAISS index, which is basically returning all the relevant documents using embeddings. And then we retrieve the relevant search results and we visualize, and we can also generate a theme cloud. So this is a basic output that we developed to start with. So you can see what kind of sentence it was, what kind of section it is appearing, who are the authors of the paper, what is the actual paragraph where this can be identified, and what are the relevant themes which are talked about in that particular data set for a particular question that user has asked. So this is a very high level view of what we are trying to do here. So essentially there are two components now. When we talk about storing the data into the FAISS or Elasticsearch, we have two stages. We have indexing stage, where from the documents we are generating embeddings, how we fundamentally store the embeddings or index the embeddings. So we are converting all the documents into individual sentences. So let's say our vector space is n sentences. Then we apply a USC on individual sentence level, so that we get 512 dimension encoded vector, and we store that encoded 512 dimension encoded vector into the FAISS index table. So ultimately the total size of the entire index or the FAISS index table comes up to n sentences into 512, because each encoding is of 512 bytes. So that is the size of the index table, and n being the number of sentences that we have across the dataset. Now when it comes to querying, we have a query text which is passed through the Universal Sentence Encoder or USC. We get a dimension encoded query, a 512 dimension encoded query, and we search it against this FAISS index table. So we try to identify what are the relevant or top matching queries against this entire document set using the technique of Euclidean distance, and we finally visualize the results. So this is basically the difference between how we index the data across the data set, and this is something that happens when the data is passed in a real-time scenario using the query. Now, just to spend 30 seconds in terms of what is USC. So USE stands for Universal Sentence Encoder. Of course, it's Google's pre-trained sentence encoding model to encode the text into high-dimensional vectors. It can be used for different use cases of classification, semantic similarity clustering. Basically, the idea here is that we use USE to convert our sentences from different documents into a 512 dimension vector embedding, so that it can be used for storing into the FAISS index table and further optimized and used for the different variety of documents. So the major advantage that USE offers is that it is also optimized and trained well for the greater than word length text too. So fundamentally, if you have a length of text which is kind of large, or if the sentence size is quite huge, USE works well on that. And at the same time, it can be of variable length. It can be an English text, and output is always the 512 dimension vector. And the other advantage that USE offered was that it occupied less space. So it occupied approximately 16 GB of data. And since we used techniques, concepts of AWS SageMaker for training our embeddings, it took around 20 minutes to compute all embeddings, which was way faster. So we used 8 virtual CPUs, one V100 GPU of 16 GB memory and 61 gigs RAM. So that is something which is basically helping us to train these embeddings in a faster manner, to kind of experiment and help us to understand how the embeddings are being generated. Then just to spend 30 minutes in terms of what is FAISS. So FAISS, as I said, stands for Facebook AI Semantic Search, developed by Facebook AI Research. It's available under MIT license. So if you're keen, definitely I would say you can explore that. And we use this tool, or let's say utility, to index our sentence embedding. So as we saw in the previous slide, that we have converted all the sentences from our documents into the encoded vector, 512 dimension encoded vector, and then we are storing it into the encoded sentence index. And then it provides an algorithm that helps us search efficiently from billions of vectors. Now, if you see, we had more than 70 million sentences, because if you are looking at 120,000 articles, you can imagine the number of sentences, because the length of these articles is huge, 5 pages, 10 pages to even 50 or 100 pages. So the number of sentences which are a part of these data sets are like quite huge. So it kind of helps us efficiently search across these billions of vectors. So that's the kind of advantage that FAISS offers. Then obviously, when we are trying to search across the billions of vectors, we have to look at the query type, because if the query, or if the natural language question that user is asking, if it's taking more than, let's say, 10 seconds, 50 seconds, or 100 seconds, it's kind of waste, because user doesn't have patience or time to wait for that long time, given the kind of compute that we have these days. So we also try to ensure that we reduce the query time so that the results are returned in quite real time. So we experimented with 3 different techniques. We experimented with product quantization. We experimented with inverted flat index, which is one of the index type. And we also experimented with IVF as 100. So different types of techniques that we experimented. So what we are trying to do is we are trying to form a cluster. So we try to cluster on all the vectors to form K clusters. So we try to determine, okay, if we have 1 billion vectors which are stored in FAISS, we convert them into K clusters, so that we try to so that when we try to search, we basically apply it on a cluster. That means we try to find the closest cluster based on the query that user has entered, and then it basically reduces that search time by K. Now, rather than looking at 1 billion vectors, we are looking at, let's say, 10,000, or let's say 100,000, or let's say a K number of clusters. So we essentially have to reduce the time by K. But again, there is a trade-off. It might happen that these clusters, some clusters may be very accurate and some clusters may not be accurate. So that's a potential trade-off with the accuracy, which we have to be careful of. So you can see the observations. So Q1 is basically question 1 with top 10 hits, question 1 with top 100 hits, and question 1 with top 1000 hits. So you can see that with product quantizer, it's more than basically 702 seconds or 780 seconds. Otherwise, in terms of IVF or in terms of IVF 100, the average amount of time required to return the results with higher accuracy is quite huge. So essentially, we try to experiment with these different techniques to ensure that the potential search time is reduced as well as the accuracy of documents is also maintained. Then we also tried to experiment with Elasticsearch as a replacement or as a potential option for FAISS, because we wanted to explore and evaluate Elasticsearch 7.x, which offers additional features of machine learning and embedding search. And it also offers additional features of improved mechanism for indexing and searching. So prior to 7.x versions of Elasticsearch, we never had concepts to search on embeddings or let's say apply some additional machine learning techniques. But I think with newer version, it offers a very improved functionality for faster searching even on embeddings of this size, let's say 1 billion or hour. So fundamentally, we indexed the documents in Elasticsearch in such a way that we had, of course, 120K articles from various medical sources. We applied some pre-processing to ensure that we don't have any junk or bad quality data, and we get the quality improved for the text. And then we extract sections as well as sentences from the documents. So we store them separately so that when we are querying when we are generating the embeddings, we have different embeddings for sections and we have different embeddings for sentences. And when we experimented with this, we identified that sentence embeddings work better. So that's why we converted sections into sentences, and then we applied embedding on top of it to generate the embedding index. So this is basically a way we want to experiment whether sectional embeddings work well for a query, or let's say sentence embeddings work well for the query. And we observed that sentences work well because sentence conveys the flow of information. It has a context related to certain section of the data. So we tried to experiment with that. If we look at the architecture when we did the Elasticsearch based indexing, we had, let's say, more than 44K. So we started with 44K because we wanted to experiment whether Elasticsearch can handle such load or not. So we got the data from various different sources. We did some text pre-processing like lowercasing, stopword removal, etc. And then we have two different workflows. One workflow is extracting sentences. So we had approximately 1.4 million sections which were stored into the section index, and sentence extractor on top of which we applied USC to identify more than 8 million or let's say 10 million vectors, because we started with 44K and now we are using this architecture on more than 120,000 articles. So you can imagine what kind of vector size it would have. And then finally, all these embedding vectors are stored into the Elasticsearch, so that what we were trying to achieve in FAISS, like searching across those embeddings to identify the relevant section or sentence which is matching with the query, we do the same thing in Elasticsearch. Now, if we try to understand this in real time, so if the user is trying to pass in a query in real time, what we are trying to do is we are basically trying to do the same technique of applying some text pre-processing, and then we have a engine which is basically splitting the text. So if the query length is descriptive, if it has more than 3 words which are making sense from a context perspective, we apply a BM25 search on the section index. We get top n sections or hits. Then we identify relevant doc IDs and we apply cosine similarity search, because here we don't have to worry about product quantization or IVF, because Elasticsearch internally handles all these kind of techniques, and apparently it uses BM25 as a fundamental utility to find the relevant data. And then we have an additional technique where we are applying cosine similarity on those sections which are retrieved using the BM25, so that we get top M sentences. So it can be less than or equal to n sections that we received, and we fundamentally visualize them. If the query length is less than 3, we directly apply BM25 on the section and we retrieve the section so that user can find more relevant data. So the more descriptive query you pass into the engine, it is quite obvious that the algorithm will understand the context from the query and it will return the relevant documents or sentences from the data. So just to spend 30 seconds in terms of what Elasticsearch and FAISS are. So fundamentally, if we compare the two different techniques, FAISS builds a semantic vector space index to identify k closest vectors to the one representing query, versus Elasticsearch builds a trie-based inverted index to quickly map a keyword to the list of documents. So essentially, it's working at a keyword level, because Elasticsearch fundamentally indexes data based on keywords. So it has a trie-based inverted index to quickly map those keywords to the documents. Of course, FAISS is vector space search. Elasticsearch performs more keyword-based search. So it is computationally less expensive when we are searching through millions of documents. But when it comes to FAISS, we have to search through different types of millions of vectors. So it can be more computationally expensive, because we saw in the previous slides that if we let's say try to get top 10,000 hits or top 1,000 hits, it might take a lot of time. So we have to use a lot of computationally high machines to get the results faster. So currently with Elasticsearch, we don't have a GPU support as of now, but with FAISS, we can use GPUs for indexing and search. So if you can basically use high-end GPUs or TPUs, definitely it can be a better technique for searching. So, so there is no direct method to reduce search time. As I said earlier, Elasticsearch internally handles searching and reducing the search time. But as we experimented with FAISS, it has techniques of product quantization. We can optimize the index size or search time. But of course, it's a cost of quality. So the more we try to optimize, it might be the chance that the quality of search may improve. And Elasticsearch can be indexed and searched. We can use basically documents in JSON format so that the document search happens on a faster manner. But in terms of FAISS, it only stores numerical vectors. So it cannot use any other document type. So that's the overall comparative study on the Elasticsearch and FAISS. Now, most important thing, how did we do on the TREC COVID, which was organized by NIST? So TREC stands for a text retrieval competition or text retrieval challenge, which was done for COVID. And it had basically 5 rounds, which had critical evaluation from TREC, which was from organizing a body. So they had human experts who reviewed the documents, who reviewed the results manually. And then they determined that, okay, these are the relevant documents. Out of relevant documents that machine has suggested, how many are correct from a human perspective? So you can see that when the machine was used to retrieve top 5 documents, the precision was more than 82%, 83%. And as we continue to add a lot of top N matching documents, it was closer to 63%. So fundamentally, if we look at this system, this is without any human intervention. So we were kind of reviewed against all the 22 submissions which were talking about completely automatic approach for doing the search and for retrieving the documents. And we were ranked 13 out of the total submissions, which were completely automatic. So we were able to experiment with different techniques. We were able to experiment concepts of AWS SageMaker. We were able to experiment Elasticsearch 7x. We were able to experiment FAISS, and it kind of helped us to learn and understand what kind of algorithms or approaches work on such huge kind of data. And it kind of was a good learning for us as well. And then finally, this is a sample view of the current system. So it is part of our COVID navigator, which is used internally. So you can pass in a query, and you can basically fire any kind of query. It can be about non-pharmaceutical, like economic impact of COVID-19 pandemic, or it can be very specific about vaccine. It can be very specific about any additional medical related data. And then we can filter. We can sort by publication date. We can sort by, let's say, arrival date, or we can sort by a certain date range to understand what kind of information is coming in last quarter, last month. And we can also look at specific publications, because users might be interested to see very specific publication houses. So they can also filter on that. So it's kind of like a state-of-the-art visualization that we develop on top of our engine, so that users can access the data in a much more user-friendly manner, and they can review the system as well. So we continue to receive the feedback, we continue to add improvements, and we continue to refine more. And then finally, we are at a stage where we are experimenting techniques of retriever and reader based on BERT for Q&A system. This is not necessarily a chatbot, but fundamentally trying to identify factual answers from the document. So it can be, let's say, what is the incubation period for coronavirus? So it's a factual answer, like 3 to 7 days, 6 to 14 days, or 19 days. So we are trying to apply such Q&A system on top of this data to determine whether can we retrieve these factual answers, apart from what we retrieved from phase 1 as the direct sentences or paragraph, which potentially are relevant to what user is asking. And then finally, we want to experiment reinforcement learning, because we want to understand what kind of user feedback we are receiving. And based on that, we want to refine or let's say retrain our system on the fly so that we can improve the search next time when the user is firing a similar query. So these are some of the experimentations that we are doing currently in terms of BERT Q&A or in terms of reinforcement learning. So we are on a journey. We are on a path where we want to take this forward so that we can learn and we can understand more. And good part is that since this is a public data, we can experiment with any different technique, because given we work in pharma organization, it becomes very tricky to use our internal data externally. But with this, I think it kind of helps us learn as well of this new state-of-the-art techniques as well. So with this, I would like to thank all of you for listening in patiently. And thank you so much, NLP Summit Healthcare, for giving me the opportunity to present here. Thank you.